He's usually the main contributor of the WMAP project. Okay. And he also the director of the Max Planck Institute for neutron physics. And then today he will talk about hunting for parity-violating physics in polarization of cosmic microwave technology. Let's welcome him.
Okay, hello. Thank you for the invitation. So let me continue on the Max Planck session following Alessandra. And I must say that I'm jealous because Taiwan is the only country where you can have real physics conference in this time. And you can actually, after my talk, you can actually go to real restaurant with real food and real drink instead of virtual restaurant, virtual drink, virtual food. So I'm super jealous, and I hope I can have an opportunity to physically go there. I've been to Taipei many times before, so I hope that I have opportunity. So I'd like to tell you about the latest work that we had published in PRL very recently in collaboration with Yuto Minami, who is currently the assistant professor in Osaka University. So basically, the topic of today's presentation would be to tell you how we might go about finding the possible parity-violating signature of the cosmological problems in CMB. And then, but I just wanted to tell you that the thing that I'm most proud of today is the development of new method that would finally allow us to do this parity violation test in the CMB that wasn't thought possible before. So not just PRL, which presented the results, but we're most proud of these 3 papers that we have written over the last 3 years that would lead to the results that I'm presenting today. So all of these papers are led by Minami, who is a leading author of all of these projects. So first paper presents the basic idea, methodology and validation, but this was done in idealistic situation of the full sky. Then we extended this methodology to partial sky and also the multi-frequency data, such as Planck. So this last paper describes the method that we used for the real data analysis that I'm presenting today. So let's remind ourselves that we're dealing with CMB, and we're living in galaxy, which becomes very important during my talk. People typically don't talk about galaxy when they talk about CMB, but the galaxy plays a big role in my presentation. So let's remind ourselves that we're actually inside of galaxy. As a result, you go to now visible to near infrared, far infrared, sub-millimeter, then finally microwave, you have this CMB filling the entire universe. Then you improve the sensitivity of your detectors a lot, you start seeing the fluctuations. Now these high galactic latitude fluctuations are coming from the Big Bang, so this is CMB. But then we also have signal coming from very nearby place, the Milky Way. Yeah, so these 2 photons come from very, very different locations. One is coming from super distant place, traveled for 13.8 billion years, and this one is basically in our backyard. So the question is, how did CMB photon travel? Okay, so this was emitted in 13.8 billion years ago. It propagates with certain wavelengths. Now, of course, as photons propagate to us, wavelength is redshifted, so the wavelengths get stretched. Okay, I'm not showing that for simplicity, but you have a redshift of the photons reaching us. But it's possible if the photons are coupled to some fields which will violate parity, the polarization direction, this oscillation direction of the electromagnetic fields of the photon may be rotated. So if it's rotated and if we can see it, that will be the signature of the parity violation. So let me just give you one example. This is not the only example, but just give you one example. Let's say you have an axiom, very popular these days, popular again. Axiom has been popular for decades, and it's popular again. And now if you have a pseudoscalar such as an axiom, it can be coupled to electromagnetic tensor F mu nu via a Chern-Simons term, which is parity-violating. Now for cosmological application, of course, we have a Professor Kim and who championed axiom as a dark matter. So that's a cosmological context. But for cosmological context, cosmological application of coupling between Chern-Simons, the coupling between axioms and electromagnetic field, I could find the turn and withdrawal as a first application. But maybe you know previous papers that dealt with such a coupling in cosmological setting. If you do know about that, let me know. I'd love to know. So this is the earliest paper I could find myself. So this turn and withdrawal studied the generation of primordial magnetic field during inflation by breaking the conformal invariance of electromagnetic fields by introducing Chern-Simons. So this term indeed violates parity because B, magnetic field, is axial vector. So this is parity even. E, electric field vector, is parity even. Now if you parity odd, if you square them, both terms are parity even. So this kinetic term, as usual, is invariant under parity flip, but Chern-Simons term, B dot E, changes the sign under parity inversion. So that's parity odd, and then as a result, this axiom field is also a parity odd, it's pseudoscalar. So this violates parity. Now, if you have that, as Carol, Field, Jacques, and then all the other authors show, this would make phase velocities of right and left-handed polarization states different. So universe now behaves like a sapphire. Now you shoot a photon with one polarization direction, and the photon goes through, the polarization direction will be rotated by beta, angle beta. The important thing is that this beta is proportional to the path length, okay? So the bigger the distance, the bigger the signal, because that's an integrated effect, okay? So emission in this case would be 13.8 billion years ago. So photons will propagate for many years to reach us. And this accumulation of the signal is what we're looking for. All right, so motivation. We don't know dark matter, we don't know dark energy. They could be axiom. In fact, both of them could be axiom. Both of them could be the same things, just different sides of the same coin, or they may interact, whatever, could be an axiom. If they are an axiom, they could couple to electromagnetic tensor via Chern-Simons term. So if you do detect it, it will be a tremendous discovery for understanding the nature of dark matter and or dark energy. So that's motivation for physicists. Motivation for simple-minded astronomer like me. I just wanted to look, okay? So universe, I learned that weak interaction violates parity. Why can't laws of physics governing cosmology violate parity? So let's look, that's all. So I look, and then this is the temperature fluctuation map obtained by Planck, removing galaxy, okay? Then if you measure polarization, you measure that. So the direction of the lines will represent the directions of the polarization, and then length will represent the intensity of polarization. And now if you look, okay, so red here, blue, red, blue, red, blue. So this looks like a plane wave going in the horizontal direction. So let's call that wave vector L. And then we're trying to figure out how polarization directions are related to the wave vector direction. So let's say you have a wave vector direction L, If the polarization direction is perpendicular to or parallel to that, we call this E mode. And when polarization directions are 45 degrees tilted, we call this B mode. Now, let me warn you that this E and B have nothing to do with electric and magnetic fields, okay? Has nothing to do with it. It's very confusing, but just take it, okay? These are, from now on, E and B are just jargons used in CMB community. It's even more confusing because if I say now that E is parity even, because signs don't change under parity inversion, but B changes the orientation. They flip the signs, okay? Unlike magnetic fields, which is parity even, B mode polarization is parity odd, okay? So sorry for the jargon, but that's the way it is. Now, then E is parity even. If you square this to define the power spectrum, it's parity even. B, that's parity odd. If you square it to define the power spectrum, that's parity even. Temperature is parity even, so temperature E is also parity even. As a result, when you have cross correlation between temperature and B mode polarization, or E mode polarization correlated with B mode polarization, this will change sign under parity flip. If universe conserves parity, TB and EB expectation values must vanish. Okay, so if you measure them, they should be consistent with zero within error bar. If they are not consistent with zero within error bar, that's a discovery of the parity violating physics in the CMB. So now, if you are not familiar with the power spectrum, let me tell you. So this is the amplitude of fluctuations as a function of angular scales, and L, the x-axis is this angular wave number. That's basically 1 nova wavelength. So if you look at the leftmost part of this diagram, you're looking at the wavelengths of fluctuations. That's as big as the sky. And as you go to the larger L, so smaller angular scales, you're looking at smaller wavelengths. Then if you have done measurements of all of the modes, you recombine if you want, you get the original map back. So that's nothing but Fourier transform done in spherical sky, okay? So that's the spherical harmonics. So now you have done this measurement over the last many decades. Cosmologists worked very hard. Then you discover the temperature power spectrum that's coming from the sound waves, and you have E mode polarization coming from also the sound waves, okay, this E mode. When this is gravitational lens, E mode gets converted into B, and that's the B mode polarization coming from the lensing. And then that's also measured. The only thing that's not measured so far is the B mode polarization from the gravitational waves. That's typically the topic I speak about at the physics conference like this one, but that I'm not going to talk about this. I'm going to talk about something that's not shown in this plot that you typically see in any CMB talks. That is E and B cross power spectrum, okay? Something that you haven't heard before. So when you have so-called cosmic birefringence, namely universe behaving like a sapphire, sapphire is a birefringent material. When you shoot light in one polarization direction, the direction of the polarization will be rotated as photons go through sapphire. So as a result, even if you had only E mode at the surface of Nat'l scattering 30.8 billion years ago, E gets converted into B. Okay, and the way it does is, for example, beta is small, so sign for beta will be 4 beta divided by 2 will be 2 beta. So you have, if you have intrinsic E minus B, such as this one, E minus B, intrinsic power spectrum, then this will be converted into observed EB by 2 times beta, okay? And if you had also the intrinsic EB, this will be transformed into observed EB times basically 1 because beta is small. So traditionally then, we assume the theoretical model for E here minus theoretical model for B here, take the difference. then try to use that as a template to fit to the observed EB and find the angle beta. That's what we typically do. Now, I can make one improvement in this methodology by relating also observed E, observed B to the intrinsic E, intrinsic B, and intrinsic EB, and write difference between observed E and B in this way. And I substitute this here. I can relate observed EB to the observed difference in EE and BB. So this is nice because we no longer have to assume a model to define, to determine beta from the observed data. That's excellent, okay? But the biggest enemy is yet to come. The biggest enemy, the reason why you haven't heard of this until today is because of the following problem. We actually can't distinguish whether the signal is due to the universe being a sapphire or rotation of the polarization direction is coming from me being rotated, okay? So I thought that my head is this way relative to the sky. I didn't know that I actually rotated my head and looking at the sky. I didn't know this, okay? Namely, I have a detector whose orientation to the polarization in the sky is this way, okay? Or at least I thought so. But when I put this detector in my telescope, I forgot that I rotated it, okay? I forgot that, okay? And I didn't correct for it. Then, even if the polarization direction is this, I mismeasure it to be that way, okay? It is perfectly okay that my head is this way, okay, when I look at the sky, as long as I knew it and I made a correction for it. But if I didn't know and didn't make a correction for it, that's a big problem, okay? So I cannot distinguish between the intrinsic cosmological birefringent signal and me being rotated. Therefore, the only thing we can measure, well, at least people thought that we could measure only sum of two angles, beta plus alpha. Alpha is a so-called miscalibration angle. So you look at the past measurements. First measurement was done by Chinese group, Tsing et al. Very nice. So then we also made a measurement using WMAP, and then lots of other people have done the measurements. If you look at all these measurements and take error bars at the phase values, you start to wonder what's going on. For example, why haven't we heard the announcement of discovery of cosmic birefringence here? You know, it's 15 sigma measurement. But also you see all these values are all over the places, and the differences are much more than error bars. That's because we're not measuring beta here. We're actually measuring alpha plus beta. So what you should do then is to make a correction if you knew what alpha was, or at least you would add the systematic error coming from your knowledge of alpha. For WMAP, for example, before we flew WMAP, we characterized the detector so that we knew we wouldn't be able to know the absolute angle of the detector to better than 1.5 degree. So when we make a measurement of beta using EB correlation, we should also add to that the systematic error coming from our lack of knowledge or our limitation of knowledge of alpha. That's the uncertainty for quad experiment. That's uncertainty for Planck experiment. In all these other experiments, the alpha error bar is not yet reported. They have some ideas, but that's not reported yet. So we're not ready to make any claim about this. But is there any way to mitigate this? And we have an answer for that now. Namely, sky contains not only CMB, but also galactic emission. And galaxy is on your backyard. It didn't propagate for 13.8 billion years. It propagated for 100,000 years or something like that. It's really, really nearby. So they don't suffer from cosmic birefringence, but they do suffer from the angle miscalibration. This is observed E, this is observed B. The foreground E and foreground B are affected by miscalibration angle, but not by the birefringence. C and B is affected by both miscalibration and birefringence. So if you use that, you can now relate measured total E and BB that contains both foreground and CMB, and that's rotated by alpha, but we also know actually something about CMB polarization power spectra. These are known pretty accurately. So we can use this knowledge to extract beta, okay? Now, however, we have to make some assumptions about the intrinsic signals. For example, intrinsic EB at the surface of lasso scatter, okay, that if you find it, that's another discovery. So let's keep it for later, okay? So I'm going to assume that this is 0, although even if it's 0, even if it is not 0, we have a way to characterize that. So, okay, but let's ignore this for the moment. EB foreground is a big issue. And for the baseline result I'm going to report today, I'm going to ignore this, but then I will make a comment on this important effect toward the end of this presentation. So if you're wondering about this, wait until later. Okay, now, so because we have the observed EB, this is a model. We just take a difference, square, divided out by the variance over the data, sum over L, that's my chi-squared. Then I minimize this chi-square by varying alpha and beta simultaneously. Now, this is true for full sky, single frequency data, but we have a way to generalize this to cut sky, massless sky, and multi-frequency data. So we do the full thing as described in the paper, but for simplicity, this is all you have to know. The way it works is very simple. If you didn't have foreground, let's say 100 gigahertz is pretty CMB dominated, then all you can determine is alpha plus beta. In other words, in this figure, this will be the dotted line, okay? This is alpha plus beta constant. If you didn't have any foreground, this is all you can measure. And indeed, in this kind of simulated data for future data sets, alpha plus beta will be very, very precisely determined. So this direction, uncertainty is almost 0. But now you have a little bit of foreground, even at 100 gigahertz. This will break the degeneracy between alpha and beta by constraining alpha with this magnitude here, okay? So degeneracy is now broken. And because alpha plus beta is very precisely determined, error bar on beta would be equal to the error bar on alpha, okay? So alpha is determined by foreground, that will determine the error bar on beta. As you go to higher frequency, you have more dust. So your determination of alpha improves. As a result, your determination of beta also improves. But if you go to too high frequency, you don't see CMB anymore. It's all dust. So you lose your ability to measure beta. You only constrain alpha, okay? So it's a very, very interesting transition from CMB dominated case to dust dominated case, and you can use this kind of behavior to nicely separate the effects of alpha and beta. So I know that this is a theory conference, so you don't want to know how we did analysis, but if there's an expert in the audience, just in case, let me tell you, and also this is important that because talk is recorded, I have to show that we have done good analysis, okay, to make the results credible. So we used 4 frequencies of the Planck data, which are polarized. Then to measure power spectrum, and without being affected by the possible noise correlations, we split data into 2. And these 2 data sets have no noise correlations between them, called these half missions 1 and 2. And we measure power spectra only from those 2 separate missions, never the same data sets, to eliminate noise correlation. We use a restricted range of multiples, 50 to 1,500, because lower multiples are known to have some contamination from systematics. and also this approximation that the likelihood is Gaussian breaks down at such low multiples, so eliminate that. These are the same error ranges used by Planck analysis, for this kind of measurement, so it's also consistent with what they used. We mask the region that has too bright carbon monoxides, which are known to contaminate EV measurement, point sources, and pixels that weren't observed by Planck. We also correct something called intensity to polarization leakage due to beam mismatch. Now that's probably too complicated, so I don't talk about it, but I just say that for experts, we corrected it. But fortunately, even if we didn't make a correction, we get the same answer. So that's reassuring. Okay, so we are not affected by this effect. This is the mask. So we retain most of the sky, unlike traditional CMB analysis, which masks about 30 to 40% of the sky, but we retain most of the sky. These funny regions are bad pixels, which are not observed by Planck during this particular half mission time. And these dots are either bright carbon monoxide regions or bright point sources. Okay, then we validated our pipeline against the simulations, and these are Planck team's simulations, which contain all the known systematic errors. So if systematic errors produce any kind of non-zero alpha or beta, we will see them in the simulation. So long story short, we don't see any spurious signals coming from the systematics, known systematics. So test has passed, our pipelines validated, now we're ready to go. So before we present the main results, so these are the main results, let me just tell you that if we assume all Planck detectors are perfectly characterized, so no miscalibration angle, we get beta that's positive at 6 sigma. Okay, so that's 0.29 plus minus 0.05. And this is already reported by Planck collaboration. This is a completely independent analysis from Planck. But of course, we wouldn't know whether this is due to beta or alpha, okay? Because you're assuming alpha here, what we measure is alpha plus beta. So then no uncertainty on alpha is 0.3 degrees. That's why we haven't yet found any signature of beta in a Planck data. Our idea is to use galactic emission to break the degeneracy between alpha and beta, so we can do simultaneous determination. And we got this result. That's 2.4 sigma positive. Okay, it's only 2.4 sigma, no big deal, no discovery, only a weak hint. But you know, it's interesting. And now if you look at alphas, that's even more interesting because apparently Planck team has done great job aligning alpha, okay, so that these alphas are well within statistical uncertainty of our measurements. Also, they're well within their qualitative systematic uncertainty, 0.28 degrees. And when you look at 100 gigahertz, indeed, you know, we do see 2 sigma alpha negative, but that 2.28 sigma is also comfortably consistent with the uncertainty of the systematics that they reported. So everything is fine, okay, as expected. Now you might wonder whether this 2 sigma comes from 2 sigma here. So we then eliminated 100 gigahertz to make sure, and you got the same answer, okay? So this is not coming from this, it's coming from all the data sets. Let me tell you that there's no one channel that's responsible for the signal, okay? All channels contribute, and we have a consistent story there. So let's see whether we see it by eyes, okay? Just to make sure, okay? So let me remind you that what's happening is this EE minus BB leaks into EB, either by miscalibration or birefringence, or both, okay? So this birefringence given by the theoretical E minus BB, C, and B, that's shown in blue, is rotated by both alpha and beta, okay? But foreground is rotated only by alpha. So this red is a total CMB and foreground. So difference between red and blue is rotated only by alpha. So if you look at EB, and if you see blowing up, blow up signal in EB at low multiples, that must be due to foreground. Therefore, it must be due to alpha, okay? So if you look at the data, we don't seem to see such a blow up, okay? We see some blow up, but the magnitude of the blow up is so small that it's only, okay, either plus or minus 0.07 degrees. But the birefringent signal that seems to present here is 5 times that, okay? So if this beta was all due to alpha, signal should be 5 times bigger than the red that we don't seem to see here, okay? If alpha was 5 times bigger, we would have grossly overestimated the signal that we see in EB, okay? So now on the other hand, if you look at EB from birefringence, because it's coming from CMB, you should see these acoustic oscillations coming from sound waves. And I mean, I don't know about you, but something may be there. Okay, it's 2.4 sigma, so okay, let's not spend too much time on it. But maybe something is there. Now, what about foreground EB, okay? We didn't talk about it. If there's an intrinsic EB in foreground, that would mess up our measurements. That's for sure. So let's say we have foreground intrinsic EB, that's positive, okay? If you didn't know it, we would misinterpret this as the positive alpha, okay? In other words, even if there is no alpha, we think there will be alpha, right? So even if we think we're measuring alpha, we're actually measuring alpha plus gamma, where gamma is a contribution from the intrinsic EB. If the intrinsic EB is positive, gamma is also positive. So let's pretend that there is gamma in the data sets. So from foreground, we measure alpha plus gamma. From CMB, we measure alpha plus beta. If we take the difference, our measurement is therefore is beta minus gamma, okay? So that's what we actually measure. If now beta was negative, we might be able to explain all the signal we see here by just intrinsic EB. So is it possible that the gamma is negative? Answer is surely yes. But interestingly, there's an evidence for dust-induced TE and dust-induced TB, both of which are positive. So if both TE dust and TB dust are positive, it's likely that EB is also positive as shown by these authors. If so, our measurement of the beta is actually a lower bound. Oh, that's interesting, yeah? We don't exclude the possibility that the gamma is negative, but so far, there's no evidence for it. If there's anything, there's evidence, or there's good argument that the gamma is positive. So that makes the whole thing even more interesting. But in any case, so now I take this Transsimon's term, writing this way. Then let's say scalar field, let's say axion field, changed over time, okay, from last scattering surface to observed, yeah, time, 13.8 billion years between them. Then our measurement is change in phi times g is 10 to the minus 2. So if you have a favorite theory, go ahead and play with it. Of course, we don't forget that it's 2.4 sigma. I spent most of my career worrying about 2.4 sigma called Nongal sanity in CMB. If you know me by chance, you might know me from parameter called FNL, and I would spend enormous amount of time worrying about 2.4 sigma for FNL, and now we don't have it. So I perfectly understand what 2.4 sigma means. So as I emphasized at the beginning of my presentation, the thing we are proud most about, Yuto, Minami, and myself, and our collaborators are most proud of the method. And thanks to this method, we're finally able to make this measurement, which wasn't possible before. A nice thing about this is that we have not only Planck, but also all kinds of other CME data sets today. So anyone can apply our method to any of the data sets that they have and immediately confirm or refute the signal that we see, okay? I mean, in some sense, 2.4 sigma can never be wrong, but in any case, it'd be good if all of the existing experiments do the same thing and they report the beta and see how they compare. If confirmed by future experiment, so good news is there are also several very powerful future experiments that are coming up, planned, funded, and all that. So by, let's say, 2035, 15 years from now, we'll have dream CME data sets. Now, this signal may disappear next year, but if it survives for the next 15 years, we will know, for sure whether this thing actually exists. So I stop here. Thank you very much.
Thank you for very last one. Any questions?
Very additional. Can I ask you about now you measure global angle? Could you tell from your analysis the angle is dominant on some scale, plane scale? Can you hear?
The scale. Sorry, could you repeat the question? I couldn't really hear.
I would say now you measure global angle. Could you tell from your analysis that the angle is dominated by some scale, larger than some L?
Larger than some scale.
Yeah. Is it
You mean multiples or which scale?
The angle is it?
Okay. Yeah.
You can see it's dominated by some scale.
Yes, here. Is this why you're talking about the scale, like angular scales here?
Yes. I mean, now you tell us that you measure a global angle. That's okay. Everywhere the same angle.
Yeah.
Rotation depend on scale or?
Okay. I think what you mean is it possible that angle depends on the position?
Yes.
Yeah. Like here. Right? Does the angle vary over sky? Is that the question?
Not exactly, but somehow it's I mean, is your angle L dependent? Maybe in terms.
Yeah. Okay. So I guess the question is whether angle either depends on position or depends on L.
Yes.
Yeah. That's an interesting question because, but okay, we don't know because it's 2.4 sigma. If you divide this into the angles, we get no sigma, right? So that's very difficult. That's very difficult to tell. However, let me tell you that this is potentially very exciting because if you look at this EB intrinsic, and if this intrinsic EB at the surface of Nat'l scatter, which we're ignoring now, came from, let's say, chiral parity-violating gravitational wave, then the EB power spectrum would look more like this. The birefringence power spectrum looks more like that, okay? So the shape is different. And if the birefringence, this EB comes actually from this, not this, this would show up as the angular dependence on beta, right? The multiple depends on beta because we use the wrong template. So interesting exercise we can do in the future even now actually, is to do the simultaneous fitting of this beta and this one here, right? We wrote a paper showing that we can actually do this. And for example, if gravitational wave came from SU2 gauge fields during inflation, you produce this, and spectrum is completely different from this. So we can simultaneously constrain this and that. So, yeah.
More question? There, question. That's not the question. It's trying to say. So may I ask a question? Can you hear me?
Yep.
So if you can measure something, they imply that the actual model was there, right? And with this kind of magnitude, do you expect some? I think people are also trying to measure axion with this kind of covering in the lab. Do you think that the implication that this kind of size can also be measured in the lab? With
yeah. So let me then actually show you. So I mean, again, I apologize that I couldn't quite hear this question very clearly, but I think I got it. And the question is, what about other measurements, measuring measure the axions, and then how are they related? Yeah, or something like that. So yeah, let me tell you. So this is not my paper, but the paper that came out one day after we posted this paper to arXiv. So you see G, that's the coupling constant between axion and the electromagnetic fields. M is the mass of the axion. Our measurements, so depending upon how much, whether our axion field, quote unquote, explain all of dark energy today or only fraction, yeah? Depending on that kind of assumption, your constraints coming from our angles will be different. And also the constraints on G will depend on how light the field is, because that will decide how much field variation you had between last scattering surface and today, okay? And this is the kind of constraint you get. And these are all the measurements that have been done so far in this parameter space. So our measurements are completely consistent with everything that has been done so far, and much, much better. Yeah. So even if our measurement, at least in this mass range, so even if our measurement turns out to be only upper bounds, we are much, much better already. And it's consistent with everything we know already so far. Yeah. So I hope this answers your question.
Yes, thank you.
Yeah. By the way, paper is this one. I should put this up.
More questions?
Yeah, in the future, the CMP experiment 10,000 many detectors. So by then, do we still worry about the alpha angle because they may average out to 0? So many detectors.
If the average angle is 0, then yeah, we don't worry about it. If this,
because the 10,000, 20,000 detectors in the future, in this, yeah.
Yeah, but what we're worried about is the rotation of the entire detector, right? Even if you have 10,000 detectors in this wafer,
yeah.
If the entire wafer is rotated, that will show up as alpha. That's what we're worried about. In fact, we never worry about how detector orientations are located within the wafer, because we know them super well. What we don't know well is this, bulk, wafer containing 10,000 detectors. How is that oriented with the sky? That we don't know so well. So this is still relevant in the future for sure.
More questions?